session, we will start with some brief introductions, like around 5 minutes top. And then our speaker, Professor Billinghurst, will give his talk, which will be around 50 minutes. Then we will have 15 minutes for questions from the audience. And just to let you know, this session is going to be recorded. I think we already started recording. Yeah, perfect. So first of all, for those of you who don't know ET, we are a Spanish private research and technology organization located in Valencia. Our focus is to bridge the gap between research and industry, providing innovative solutions and services that allow us to capture innovative solutions and services in different core areas such as advanced analytics, artificial intelligence, IoT, cloud, and also providing solutions for areas such as manufacturing, society, or health. Last year, we started the project HCIHEALTH, in which we are focusing on human-computer interaction methods to design and develop systems aimed to support mental health and well-being. And we are currently exploring different IoT devices that allow us to capture relevant information from the user, which will help us to identify digital biomarkers of mental health disorders. And the final goal is to put this together in an interactive system to support mental health. And one of the technologies we are currently exploring within the project is augmented reality. And today we are really happy to have here with us one of the world experts in the area, Professor Mark Billinghurst. Mark Billinghurst is Professor of Human-Computer Interaction at the University of South Australia in Adelaide, where he leads the Empathic Computing Research Lab. He has published over 450 research papers, which is like really, really impressive. His previous research is on wearable computing, mobile interfaces, virtual reality, collaborative systems. And he has also received many awards, including the 2013 IEEE VR Technical Achievement Award for his contributions to research and commercialization in augmented reality. Also in 2012, he won the 10-year Lasting Impact Award for the most influential paper published at the ISMAR conference. And also in 2013, he was elected as Fellow of the Royal Society of New Zealand. These are just a short list of his achievements. We could spend the whole hour listing all of them, but we do not have time for that if we want to hear Mark. So I will now stop sharing my screen so that the speaker could share his slides. And then the floor is yours, Mark. Thanks for being here today.
Great. Thank you very much for the opportunity to speak to you. Let me just share my slides. Okay. Can you see okay?
Yep.
Great. Okay. So it's a really great pleasure to be here. I wish I could be with you in Spain. As I was saying just before, I was in Valencia, boy, about 15 years ago now, and it's a very fantastic city to visit. I would love to go back. And so I'm going to be talking to you today about augmented reality, and especially focusing on the future of augmented reality and what important research directions there are. So first of all, when I was born in 1967, this was the most popular computer on the earth. This is the IBM 1401, and at that time, half of the computers in the world were this model. And as you can see from the picture, it took up a large room. And in fact, in those days, you could not buy the computer, you had to rent it. And you paid $10,000 a month to rent the computer. And in 1967, $10,000 a month was the same price as a house. So it's very, very expensive. Of course, in the 50 years since then, computers have changed a lot, and we've shrunk them down. And now we have things like Google Glass, where you can wear a computer on your head. So we have this trend of computers going from room size to desk size to then on your lap, in your hand, and now in your head and on your wrist. The way we interact with computers, though, still has not changed a lot. The traditional way, of course, in recent times is using a graphical user interface. And so there's always a separation between the physical world and the digital world. You sit on a screen, and the screen is like a window into the digital world. So one of the goals of computer interface design is to try and to make that separation go away and make the interface invisible. And there are a number of ways that you can do that. Here's a picture that shows several of them. The yellow there represents the computer space, and the R represents the real world. So one of the ways to make computers go away is to embed them into the real world. And this is commonly what we call today the Internet of Things, where you've got smart devices around you, like a smart speaker or thermostat. And of course, in this case, the physical computers disappeared into our surroundings. A second way is through virtual reality, and of course most of you are familiar with that. Virtual reality is where you put the headset on and use goggles and gloves, and your real world becomes replaced by a computer-generated environment, and you have these key properties of immersion, interaction, and imagination. But the main thing we're going to talk about today is augmented reality, and with augmented reality, of course, the idea is to keep on interacting with the real world, but to have your interaction with the real world mediated through a computer. So the virtual images are blended with the real world. So there are really three key properties of augmented reality. One is that you can combine real and virtual images together so that they both can be seen at the same time. Secondly, the virtual content can be interacted with, and so the virtual content can be manipulated or somehow changed in real time. And thirdly, the content is registered in 3D, so it looks like it's fixed in the real world. And so I want to show you a short video clip of a company that spun out from my lab in New Zealand. And this is it shows a typical augmented reality type experience that's running on a mobile phone. So in this video, what you will see is a person coloring with coloring pencils on a McDonald's playmat. And so with this technology, you can color the page in, and then you can use your phone to look at the page, and then the page comes to life and you can see an augmented reality character popping off the page. The special thing though is that the character takes the colors that you've colored on the page, so you can make a personalized 3D model. This is an app called Quiver Vision that you can download for free on the App Store. But it has many of the features you see in augmented reality. You can see that you have the virtual content is blended with the real world. In this case now you can see the virtual content looks fixed in the real world, and you can interact with it in some ways as well. So we've talked about three things: the Internet of Things, augmented reality, and virtual reality. And you can arrange these three things on a continuum depending on how much they replace your view of the real world. So on the right-hand side, virtual reality replaces everything. Left-hand side, Internet of Things is replaces almost nothing in the real world, and augmented reality is in the middle. And this is commonly called the mixed reality continuum, which may be a term you've heard of, that was developed by Paul Milgram 25 years ago. So augmented reality is not a new technology. Over the last 50 years, we've gone from bulky head-mount displays to devices being used in the military to backpack computers and then things you can use and hold in your hand. And so basically the technology's moved from the research lab and military into the living room. And in fact, if you have a mobile phone in your pocket, it almost certainly can be used to provide an augmented reality experience. So there are many, many experiences available today, from mobile phone applications where you can place virtual furniture in your real room, to design applications where you can wear headset displays, to seeing content around you can design in a very intuitive way. The market itself is very big, and there are many available devices that you can use to experience augmented reality, and a very large number of developer tools and a large number of apps and developers. And there's also a very strong research and business community. So the ISMA academic conference is the main augmented reality conference. And then we have other conferences like AWE, or organizations like augmentedreality.org that foster and grow the business. So we can see augmented reality has come a long way. And what I want to talk about a little bit about what is the future. Niels Bohr, the physicist, said that prediction is very difficult, especially about the future. And then one of my favorite designers, Bill Buxton, he says that the technology that will significantly affect our lives over the next 10 years has already been around for about a decade. And the future is with us. The trick is learning how to spot it. So it takes about 20 years for technology in the lab to enter the living room. And so what I'm going to show you today is some technologies that are on the verge of becoming popular, and some of these technologies may affect the augmented reality experience in the future. So if we return back to the three key enabling technologies, we had combining real and virtual images, interactive in real time, and registered in 3D. These three technologies areas are also important areas for research, and these three characteristics of augmented reality specify what type of technology we need to have. So for example, combining real and virtual images means you have to have some display technology. Being interactive in real time means you need to have some interaction technology, and registered in 3D means you need to have some sort of tracking technology. So I'm going to talk about each of these three areas, and then also some other areas of importance for the future of AR. So first of all, with displays. So with the display technology, we've seen an evolution from very bulky head-mount displays in the past to currently we have handheld and lightweight head-mounted displays, and in the future we'll see more wide field of view head-mounted displays or innovative displays like contact lenses that might be used. So as an example of that, you can see in this picture here, the top pair of glasses is called the Loomis DK40 from a company from Loomis, which is an Israeli company. And they now have been developing waveguide techniques that let you build wide field of view displays that are more socially acceptable. You can see the person wearing a pair of glasses, and they're almost something you can wear every day. But these displays still typically only have 30 or 40 degree field of view. So some research being done at Nvidia and University of North Carolina explored how to make wider field of view displays, and that's the display on the bottom. And this combined an LCD panel with some small point light sources. So basically they took a panel, put small holes in it, and then each of those holes acted as a lens, and they could then widen out the field of view. And this supports a 110 degree field of view display, which is very wide for an optical see-through display. So this video shows it working. You can see in the video the text appearing in the real world, and it looks like a very wide field of view display. This is 110 degrees, which is about the same as what you get in a VR headset like the Oculus Quest. This same approach has been commercialized. So this is from a company called Cura, and in Cura they have these small, if you look very carefully, you can see small spots on the glasses, and these are little mirrors, and these also provide a very wide field of view, and they say they can achieve 150 degree field of view in a very transparent screen, and also very high resolution. So this is the type of glasses we might be wearing in the next few years. But of course, the vision is to get rid of glasses entirely, and there's been some research being done with contact lenses. About 10 years ago, Babak Parvez at University of Washington developed one of the world's first contact lens displays, and he used MEMS technology to build very small components that would fit into a contact lens, and was able to provide power and data and a small display. More recently, the company Mojo Vision has been developing a prototype of smart contact lens. You can see that on the bottom right. This is what the Mojo Vision display looks like. It combines a prescription contact lens with some electronics that provide power, sensors, and communication. Then on top of that, a cosmetic lens that gives you an iris, and then finally the plastic the platform on top of that to protect it. So I want to show you a short video where they talk about the technology behind this, and you can see how this might change how we have augmented reality experiences in the future.
Building the world's first AR contact lens is a systems engineering problem. And therefore, we've had to innovate in many different areas. For example, displays, optics, wireless communications, sensors, and materials, all while keeping the system small, low power, and of course, safe. We embed all of our smart components into a time-tested contact lens platform called a scleral lens. A scleral lens rests on the white part of your eye, and it doesn't touch your cornea. Now, what we do is we custom fit each lens to your eye so that it's extremely comfortable to wear and doesn't rotate or slip on the eye. We've also patented a method that maximizes the oxygen delivered to your eye, which is another critical element of contact lens comfort and eye health. The Mojo lens includes thin film, biosafe batteries to power the system, as well as motion sensors to enable the world's most accurate eye tracking. We've also developed an extremely low power image sensor that's used for computer vision and scene detection. But at the heart of the Mojo lens is the world's smallest and densest dynamic display. The pixel-to-pixel spacing in our display is only 1.8 microns, giving it a density of 14,000 pixels per inch. With this, we can display crisp text, photos, and video in a package that's less than 0.5 millimeter in diameter. Now, on top of that display, we put an elegantly complex multi-surface micro-optic that we make out of a single piece of plastic. This micro-optic focuses light from the display directly onto the retina. So sometimes we get asked, won't the system block your natural vision? And the answer is, of course, no. It turns out that the display is so small and close to your eye that your eye essentially looks around the display. It's the same principle at work in a Cassegrain telescope like the Hubble. Our current system delivers a monochrome green image, but we're also...
Okay, I'll stop the video there, but you can see it's a really amazing technology that's been squeezed into a contact lens display. But it may be 10 or 15 years before we start wearing this on an everyday basis, because there's still significant challenges that they have to solve. But they're saying they're going to bring this to market next year for people with certain visual disabilities. For example, if you've got low vision problems, they can use this to help enhance the edges of real objects you can see in the real world. So there's some trends happening in the display space. If we look at interaction now, over the last 20 years, interaction has also evolved with AR. 20 years ago, it was really very limited interaction. You have a handheld display, you could move around, and you could see objects that appeared fixed in space. But now we have the ability to support some simple gesture interaction, or with a mobile phone, you can touch on the touch screen. And in the future, you'll have more natural gesture-based interaction, and including multimodal interaction with speech and gesture together, and very intelligent interfaces. So there's been some amazing work being done in gesture tracking over the last few years that we're starting to see now appear in head-mounted displays. And this includes using depth sensors to capture your hand gestures and support very rich two-handed gestures. And companies like Microsoft and Oculus are starting to bring those into the headset. So here's an example of a typical hand tracking that might be in an AR system. You can see a virtual menu that pops out of the person's hand, and you can use your other hand to interact with the virtual menu. And in fact, you can pull the tabs, and you can have occlusion between the real hand and the virtual hand as well. So it supports very natural, intuitive interaction. One of the challenges with this, though, is that with cameras and depth sensors, you can only track kind of large hand motion. So in our lab, we did some work a year or two ago looking at how you can combine technologies together to support both large-scale gestures, but also micro gestures and fine-scale gestures. And so we looked at how we could use the Google Solly hardware, which is a small radar that can be worn on the body, and combine that with a Leap Motion, which supports hand tracking. And the two of them together provides both gross and fine-scale micro gestures. So this video shows this working. So this is the Google Solly hardware and it's also mounted with the radar with a Leap Motion, and this is combined onto the HoloLens. And you can see the person's making hand gestures on their side, and then they make small micro gestures with touching the fingers. So we can grab an object and move it around and place it in space, and then when we want to fine scale position it, we just stroke the finger against each other, and we can rotate the object in small fine scale motions. And so by combining hand tracking with this radar tracking technology, we can support much more intuitive and fine-scale interaction. Here's a second example of it being used for virtual puppetry. So you can see a virtual puppet in the real world, and as you move your hands across off your wrist, you can control the animation speed or the direction that the puppet is working in. Another very exciting technology is eye tracking, and we're starting to see head-mount displays now with eye tracking integrated into them, but there's a lot of research questions that need to be solved. So, for example, how can eye gaze be used for interaction, and how can you have very natural input metaphors? One of the challenges is getting over the Midas touch problem, and the Midas touch problem is that you don't want to select everything you're looking at. And so a couple of years ago, we did a project looking at how we could develop a system called Dura reticles that used multiple tracking modes to support more natural interaction. And in this case, we had a system set up where you could, as you move your eye gaze around, a yellow cursor followed your eye gaze, but we had a second cursor, a green cursor that had some inertia, and it would lag behind. And when the green cursor and the yellow cursor caught up, that's when the selection would happen. And so by doing that, it means that you could deliberately select objects just by resting your eye on them and waiting for a fraction of a second. So this video shows it working. You'll see the person selecting vehicles by looking around. You can see the yellow cursor jumping around all the pictures, and then when the eye rests on a picture, the green cursor moves and catches up to it, and then they select that picture. So eye tracking is one example of how you can use a physiological sensor to provide input, but there's a lot of other sensors you could use as well. And physiological sensors are very important because they allow you to provide support for implicit input, which means that you can have systems that recognize the user's intent or activity. So, for example, you can have EEG sensors that recognize your brain activity, or EMG sensors that recognize muscle activity. So this video here is going to show an example of using EMG in a simple game. The black box there, when he puts it against his arm, he can measure the muscle, the electrical activity coming from the muscle. So as he tenses his hand, you can see the signal there on the top. And what he's going to do now is put this into an AR system that allows him to play a game. And so through the HoloLens, he can see these virtual cubes appear. Then when he makes a pointing gesture with his hand and makes a fist, it will shoot out a fireball into the AR scene. So this is one way that you could support a kind of a natural, intuitive, implicit gesture. Another very exciting area is using EEG, and there's a number of companies now that are producing consumer-level EEG that can be integrated with head-mount displays, and one of them is called NextMind, and this company provides an EEG attachment that you can attach on the back of your AR or VR head-mount display, and then it measures your brain activity, and as you concentrate, you can cause actions to happen in the world. So in this little demonstration here, you'll see the person who is going to be concentrating and shooting or destroying aliens. So you can see as he looks around, he can look at the alien and then just concentrate, and it sends out kind of a thought wave, and it destroys the alien just by his concentration level. So this measures the alpha power of the brain, or the alpha wave level, and at the back of the head with the electrodes. And then one of the areas of work we've been working in is multimodal input, so combining speech and gesture together. And it turns out that gesture interaction is very good for qualitative input, so being able to grab and move objects, whereas speech input is very good for quantitative input, so specifying color or numbers or very precise input. And by combining them together, we've did some studies, and we found that people are able to complete tasks a lot faster and with less errors. So in the next video clip, I'm going to show you a system that does that. And what they do in this case is it's an augmented reality design software, and they use speech to set the mode that they're going to interact in, and then finger gesture to be able to interact with that mode. So you can see here. So now he's drawing an object shape, and then you can see the object appearing, and now he can grab it, manipulate with his hands. So now he said extrude solid, so he'll draw a shape here. The shape will be extruded. And then he can see this. So you can see by using speech and gesture together, he's able to easily complete these multimodal commands. And then one of the future directions is to build more intelligent interfaces. We did some work about 5 years ago looking at how we can combine augmented reality with intelligent training, and we found that when people did that, the system would automatically recognize when you're making mistakes and provide corrective feedback, and people could perform training tasks faster with much better attention. And people are now looking at how they can build augmented reality intelligent avatars, and you see these characters come into the real world that you can interact with using speech and gesture. So this video is going to show an example of one of those characters. This is from the University of Southern California, and you can see he points at a chair, clicks on it, and this virtual character walks down and sits in the chair, and then he will ask some questions or talk to the character.
I would like to know how it can see.
So you can see he's able to ask a question and the character responds, and also as he moves around, the character turns to face him and always looks at him as well. So the last area I want to talk about is tracking, and over the last few years we've seen tracking go from location-based and using quite crude visual markers to now when we have very good tracking systems that can look at natural, very complex printed images and track from that. And in the future, we'll have technology that can calculate camera position just by looking at objects in a scene and tracking off the models. So model-based tracking means that now if we know the shape of a 3D object, we can track from it. And in fact, recent research has enabled us to track from deformable or flexible objects. So here's an example of a piece of paper. And as the person bends the paper around, you can see they can track the paper as it's bending. And then people now are also looking at how you can track from the environment. So as you have depth sensors on your devices, you can scan them around and you can track in a very large scale environment. So for example, the iPad Pro has a LiDAR scanner and it uses laser to scan. And with the iPad Pro, you can get results like this. So this is a person's scanning the real room with their iPad, and it's producing a 3D model of the objects in the room, and then it combines it with imagery from the camera, and then in a short amount of time you can make a 3D copy of the real environment. Recently, researchers have been looking at how they can do the same thing for capturing dynamic moving objects and people. And so Microsoft developed a system called Fusion 4D where you could use multiple depth sensors and some machine learning to capture people in real time. So you'll see in this video here, an example of this working. And so you can see this person doing karate, and you can see on the screen there a 3D model of him that's mimic his behavior. And in particular, look at the clothing. You can see how the clothing is doing a very nice job of following his behavior around. And so what happens is they have a point cloud for multiple cameras, which you can see on the left, and then on the right, this is the output, which is the reconstruction. So they take the point cloud data, they clean it up, and they feed it into a machine learning application, and then from that they can segment the person out and produce the final result. I'm going to fast forward a little bit, so I want to show you some more results. So this figure back here, actually, I think it's this one. Yes, just back a little bit. So in this case, you'll see this lady dancing, and you can watch her skirt, and you can see the skirt is very well reconstructed in 3D. So it's quite amazing tracking performance. People have also been looking at how you can do tracking in the cloud. So as you capture multiple images from especially mobile devices, you can upload them to the cloud, and then in the cloud you can stitch all the images together and create a very large 3D model. And so there are a number of companies working on this. So here's a video from the company 60.ai. Actually, 60 was just bought by Niantic Labs last year. So you can see 4 people walking around this office space. And as they're walking, they are streaming 3D images from their video from their phones into the cloud, which is doing a 3D reconstruction. And then they can use the cloud services to create a 3D model. So you'll see in a second the model that they have made. And this enables us to do then wide area tracking. You can now walk around a whole building and track your location, or walk around outdoor space. So here's the reconstruction of their workspace. And the last thing I want to talk about is wide area tracking. So there's been some research done on how this can be extended out into a campus scale tracking. So if you take panorama images and walk out in the real world, you can capture 360 video. And from this video, you can record significant visual features like the edges of trees or of windows. You can combine that into a point cloud, and then later on, when you go with the camera to that same location, you can use that point cloud data for tracking. And this was developed in the University of Southern California in Santa Barbara, and they were able to track accurate to about 20 centimeters over a whole campus. So you can see in the video the system working here. So there's really 2 parts. The first part is capturing, and then the second part is tracking. So the capturing part uses an omnidirectional video, and it happens offline, so it takes a long time to process the video. So here's the person walking around in the real world with the 360 camera and processing the video. And then you'll see in the video clip here these green points that appear, and the green points are the visual features that can be tracked. And so that creates this 3D point cloud. And then the second part is the tracking. So you go back to the same location, you can download that point cloud, and you can use that point cloud for tracking in the real world. So as he moves his iPad around, he sees all these green points, which are the tracking features, and then he's able to put a 3D model in the place and walk around the model. So there's a Star Wars model he's able to show. So so that shows you the tracking, and I've talked about now display, interaction, and tracking. So I want to show you a little concept video of how it might all be put together. And this is from Qualcomm. It shows how their new XR2 chip could be used for creating enhanced augmented reality experiences. So this is the new chip that's going to go into the latest generation of head-mount displays. And with this chip, you can have 7 cameras that input at the same time and support very high-resolution 360 video and also high-resolution displays. So it can provide a true mixed reality experience. And so you can see some examples here. There's a boy running upstairs, and the stairs turn into some sort of 3D reconstruction dungeon or play space. And you can go into his room, and it automatically maps the room. Now it can dodge this and play a game in the real world. Here's a person who is having a business meeting, and remote people appearing as life-size avatars, and they can now discuss this video they're trying to design herself. There's a person who's outdoors, and with the 5G, they can have a high bandwidth shared social experience and play together. So you can see, and this is an example, another example of an intelligent agent assistant. The person's interacting with the voice, and this is a remote guided instruction where the person's trying to fix something, and a remote person is showing them what to do. So there are many possibilities. I wanted to spend the last few minutes talking about some research directions. And so researchers needed in many areas to make the vision that Qualcomm showed become a reality, especially in areas of social acceptance and cloud servicing, authoring tools, and in collaborative experiences. So I'll skip through those quickly. So in terms of social acceptance, it turns out that people don't want to look silly. And so a survey was done a few years ago of adults if they would want to wear augmented reality displays, and only 12% of 4,500 adults said they'd be willing to wear these AR glasses. And 20% of people who'd used mobile AR experiences said that they were experiencing social issues. Like when you hold your phone up and wave it around, sometimes people think you're taking a video of them or taking pictures of them rather than using AR. So as an example of some of the challenges of social issues, here's a video from a company called TAT, and what they made is a little app that lets you recognize people and overlay information on them. So here's a person getting up in the morning and he's changing his work profile from, he's a party last night, now he's going to be in business. So he opens up his phone and he puts, he's changed his social tags to more business appropriate. So he changes it to LinkedIn and SlideShare and other social tags, and then he's going to go to a business meeting. And at the business meeting, people in the meeting can pull out their phones and they can look at him and they can see these tags floating around his face, so they can get to know what his name is or his contact information. So this sounds like a really great idea. If you go to meetings and you meet strangers, sometimes you forget who they are, and so if you pull your phone out and you can scan their face, you can then be reminded who they are. So this lady is now scanning his face, and then you can see the AR tags appearing, showing who he is. So it sounds like a good idea, but when you think about it in more detail, you think there may be some problems with this. So, for example, somebody said that, well, if somebody scanned me, it might make me feel like I've been stopped by the police for identity. You can imagine if you're in a business meeting and somebody you don't know across the table pulls their phone out and starts filming you, how you'd make that feel. Another person said, anyone pointing a device in my direction to identify me better be prepared for either a lawsuit or a punch in the face. So you can see, we can technically do these things, but we have to think more about the social elements of them, and oftentimes it's these social elements that cause problems around acceptance. Another big trend is cloud services, and especially 5G. And so Nvidia, for example, just this last week, they released this Nvidia Cloud XR service, and this allows you to do augmented reality in the cloud. And then when you combine 5G plus massive graphics and server capability, you can provide really photorealistic rendering on a quite low-end device. So you can have your mobile phone or your cheap augmented reality headset and see photorealistic content that's being live streamed from the cloud onto your device. So it really provides AR as a service. So here's a video of how that might look like. This is a VR experience, not an AR experience, but it shows what it might be like. So you can see in this clip here, you've got this VR experience, but the video is almost photorealistic. And so all the graphics rendering is happening remotely, and it's being streamed with very low latency onto your device, and you can see the fantastic visual quality. And the same thing can happen with your AR experiences. So what that means is you'll get this device evolution where, today we've got these viewers, like VR and AR viewers, that are plugged to our laptops or mobile phones, with some standalone viewers. In a few years' time, we'll have completely wireless viewers that will have all the data wirelessly streamed to it. The final area I want to talk about is collaborative technology trends, and that's an area that I'm really excited about, and we do a lot of our work in our lab. And so really, in the collaboration space, there's kind of three trends. Improved content capture, so you've got to be able to capture your spaces, like I just showed you some examples of capturing your surroundings using laser scanning. Increased network bandwidth, like with the 5G, and also implicit understanding. So now we've got devices that can recognize our behaviors, like I showed you with the EMG. And when these three things come together, they combine in this area that we call empathic computing. So my lab is focusing on research in this area, and the question we're trying to solve is, can we develop systems that allow us to share what we're seeing, hearing, and feeling with others? So as an example of that, a few years ago we developed the empathy glasses, and the empathy glasses we combined together the eye tracking, display, and this hardware called effective wear hardware that can recognize your face expression into a single package, to basically allow us to share the same communication cues remotely that we do face-to-face. So cues like eye gaze and face expression, the implicit cues. So on this slide here, on the left-hand side, you can see the video view of the person who's streaming from the glasses. And on this video, there's two important things. This green dot here is the pointer of the remote person. So they can see video from your camera, and they can then point with their mouse, and you can see it back in your headset display. But the more important thing is this red dot, which is the eye gaze of the person wearing the technology. So now the remote person can see where you're looking, and that can provide an implicit communication cue, because people always look before they act. So let me show you a video of this working. So in this video, you'll see a person wearing the system, and on the right-hand side, they are assembling some blocks. And the video is being streamed to a second person on the left-hand side, and this person is going to guide them on the block assembly. So you'll see the person starts moving the green pointer around, and the red pointer starts following, which shows that he's paying attention because he's looking where the other person's pointing. So this changes how we do remote collaboration on physical tasks, because now we don't have to give a command and wait for the person to follow. We can just look to see where they're looking and see what they're about to do. And we also combine a heart rate sense and face expression, so we could then know what face expressions the person was conveying. One of the new projects we're doing, though, is looking at how we can measure brain activity to look at how we can create new types of collaborative experiences. And in particular, about 10 years ago, 10 or 15 years, people discovered this unique phenomenon happened with the brain. If you have two people doing the same task, then you have this thing called brain synchronization, which happens, which means that the electrical activity of both the people's brains sometimes becomes in sync. And when you get more brain synchronization, people think they're collaborating better. So as an example, here's the two people's heads, and the black dots there show where EEG electrodes are placed on the head. And this is before they start a finger pointing exercise. So they sit opposite each other, they point their fingers at each other, and then one person starts moving their finger around, the second person follows. So they do that for a minute or so, and then they stop moving. And then when they've stopped moving, we measure their brain activity again. And in this case, we found this. And so what you can see now is these arcs appearing, and these arcs show two electrodes that have the same phase, that become in sync now. So that means that one person's thoughts and actions are starting to influence the other person. So this is a very interesting phenomena. And then last year, we were the first group to try and reproduce this in virtual reality. So here's the virtual reality setup. We've got two people sitting opposite each other in VR. And then in the VR space, they can see each other, facing each other with their fingers moving. And you can see as one person moves their hand, the second person follows. Now, of course, because it's VR, you can put yourself inside the other person's body and do things you can't do in the real world. So this is what that looks like. And you can see in this case, you look down, you see two pairs of hands. And we did this because we felt that if you're seeing the same communication cues or same perceptual cues, that might encourage even more brain synchronization. And what we found was that it did indeed happen. So here's the two brains, and these light blue lines are showing that before we start the task, there's a little bit of random synchronization happening. But when we've done the task, you see these dark red lines that show a lot more synchronization between the electrodes. This is still a work in progress, so we're still trying to look at how VR and AR could influence brain synchronization and make people feel more connected. So just to finish up, there's a number of important technology trends that are happening in the space. Trends towards more advanced displays, towards real-time space capture. So in the next few years, you have to have a real-time device where you can walk into the real world and immediately capture your surroundings. More natural gesture interaction, better eye tracking, and especially, like I've just shown you, technology for measuring your brain activity or your emotions. And all these things combine together to what you might call empathic teleexistence. And the goal of empathic teleexistence is to have people moving from being an observer to a participant with each other, and to change the communication from explicit to implicit communication and feel like you're really doing things together. So people have been working on this for a while. In fact, there's been some research done in Japan and other places where you can take one person and put them inside the body of a robot and have them have a teleexistence experience. So as you look around in the real world, you're looking through the eyes and hearing through the ears of a robot that's remote. And this may seem like science fiction. In fact, about 10 years ago, there was a very bad movie developed called Surrogates that presented this as a science fiction experience. Let me show you the video clip here. So in this movie, what you'll see is in the future, people will buy cheap robots and they basically experience the real world through robots and virtual reality. So you've got these robots and they look very beautiful and they walk around the real world. Here's Bruce Willis, the star. He goes into virtual reality and he then inhabits his robot body. So here's the robot body of Bruce Willis that has, a full head of hair, looking very good. And then you do things you wouldn't normally do in the real world, like jumping off a building like this person here. And normally, of course, you can't be hurt at all because the robot is the one that has all the damage. But in this movie, the robots start getting killed. And for the first time, people in the real world start dying as well. And so the movie is basically a mystery just to solve why this is happening. It's not a very good movie, but the science fiction concept is really interesting. And it may seem far-fetched, but actually there's companies that are working on this now. So this video is a clip from a company called Teleexistence. It's a Japanese company, and they've developed a VR robotic system that does pretty much what the surrogates show. So here's a person going through and selecting an experience. They put their VR headset on, and then they inhabit this real robot body. And this real robot is in a surf shop in Hawaii, so he can walk through the surf shop and look at the surfboards, and then he can make a purchase of the surfboard and talk to the shop owner. In fact, he can even feel the board, and he's got these tactile sensors on his fingers to help feel it. And then once he's done that, he wants to share another experience, and so his son is going to come down, and his son can now join him, and they can pick a location to go together. So in this case, they're going to go to visit the cherry blossoms in Kyoto together. So these robots are very expensive, more than $100,000, but the model isn't to buy the robot, it's to rent time on the robot. So now, they've done the cherry blossoms, so now they're going to go into outer space. They click that, and they can jump into a robot, which is now in the International Space Station, and they can see the world from outer space. So you pay a few dollars an hour, and a minute, and you can jump into the robot. So just to wrap up, I've talked about how AI is becoming commonly available, but in order to achieve significant growth, there's still research problems that AI needs to solve, especially problems around display interaction and tracking and social acceptance and collaboration tools. This talk is a version of a paper I just recently wrote. So if you're interested in finding out more, you can download this paper. Just look for Grand Challenges for Augmented Reality and talks a bit more in detail. And if some of you are students, I should mention that we have internships available right now in our lab, virtual internships, so you can collaborate on some of these projects without even having to leaving Spain. We do this remotely. And then the final thing I should mention is that this presentation has been sponsored by the ACM, which is the largest computer society in the world. And so thanks to them, I'm able to participate in the Distinguished Speakers program, which is supported through them. So thank you very much for your time. This is my contact details. As I said at the beginning, if any of you would like copies of the slides or presentation, just send me an email or message me on Twitter. And if you visit the lab website there, you can see more information about the type of projects we're working on. So let me stop sharing, and I'm happy to answer some questions now.
Thank you so much, Mark. So now we'll open the floor for questions from the audience. You can raise your hand using the Teams feature, or even write the questions on the chat if you prefer that way. We will make sure to unmute you so that you can turn on your microphones. So Francisco, let me see if I can unmute you all at the same time, and then you will be able to just should be able now. Francisco Paco Barrena.
Hi. Hello. Thanks, Mark. Your talk was awesome. Thank you very much. And I'm more near to the cybersecurity stuff, and my question is the following: we have so problems to protect normal infrastructures. What do you think regarding the cybersecurity protection and in this? For example, in the example of the robots being controlled remotely.
Oh, I think there's huge cybersecurity issues, and so it's going to be a very important area to be doing research. Obviously, for example, if you're doing telepresence in a robot, if somebody can hack into the robot and start doing things that you shouldn't do, then that's a problem. If you if you start sharing your physiological data, your brain activity or your heart rate activity over the web, and other people can get access to that data, that could be a big problem as well. We don't do research in my lab on cybersecurity, so we're hoping that people like yourself will solve those problems, and we can just add an AR interface on top of what you're doing. Because of course, there's a huge amount of research being done in cybersecurity for the cryptography and for financial transactions and health transactions that have already been doing around the world. So we think that AR could be a layer on top of that. But there are definitely big issues around privacy and other things as well that need to be solved.
Thank you very much, Mark.
So, any more questions? I have a question myself. We are, if I can just jump in, we are currently working with EEG devices, and
right.
I really like the one you show, which was integrated within the head-mounted device, because we struggled when we started. We are collaborating with clinicians and psychologists, and either you go to a really complicated setup for these devices so that they have very good tracking and accuracy. And it seems that if you move to these headbands, which are smaller and more easy to just place them on the head of the user, it seems that the accuracy is not so good for certain tasks. Not sure if you have any advice on the topic.
So yes, EEG is very complicated, I would say, and so what we've been doing, we've been using several devices. So we've been using the brain cap type devices where you can have a full cap and you can use either dry or wet electrodes to do the EEG measures. Sometimes it's quite difficult to wear those devices at the same time as a VR headset or an AR headset, because you cannot physically put them both on together. But we're trying to address this problem ourselves. We're doing some research in our lab now on looking at fabric-based EEG electrodes. And it turns out in the university across the street from us, they're very expert on electronic textile. And they developed some work building medical sensors that are flexible, especially for ECG, so measuring heart rate. They built a T-shirt you could wear that will measure your heart rate. And we're collaborating with them now to be able to build EEG electrodes into fabric as well. And so we think if we can build that into some elastic and then wear it as a tight headband, then you may get better results from that. So I should say that now you can, next month you'll be able to buy a head-mount display from Hewlett-Packard that has physiological sensors integrated into the display. That has heart rate sensor and eye tracking into the display. And there's a company called OpenBCI that makes open source EEG hardware, and they are going to produce an integrated EEG and physiological sensor head mount next year. So it'll combine EEG tracking or EEG data collection with eye tracking and with heart rate. And that's called the Galea project, GALEA. And that will become available early next year. So you'll start to see all-in-one devices that will help get around that, and they can be used by clinicians in a clinical setting. But it's still an important problem that has to be addressed, I think.
Thanks a lot. That's super helpful. We'll check those as well.
Yes, if you send me an email, I can send you links to some of the products that I mentioned.
Cool. Thanks a lot. So do we have any more questions, either on the chat, or you can just unmute yourselves and share your thoughts? I see Jose.
Hi. Thanks, Mark, for your presentation.
No problem.
I would like to ask you about some kind of difficult predictions about right now. If not all, most of the devices or experience with VR or AR are wearing a device for each person.
Yes.
Do you think that we can foresee a near or medium distance future where we have we could have a shared experience between a certain amount of people where they will share an space but without wearing a personal device?
Well, that's a good question. Already, you can do that with some projection technology. So a number of companies and researchers are developing shared projections. So you can have a room, you walk into, the project onto the walls, or you can project on the table, or you can project onto, some other surfaces and have a shared experience like that. But of course, you still have to have projectors, and that's not necessarily very portable. But that's possible now. In the talk, I talked about contact lenses, and you could imagine in the next 20 years, potentially, where you have everybody's wearing small contact lenses, and you could then create a shared experience using that. But then, of course, you have to have the contact lenses in your eye. So you'd have to have some sort of device, whether it's either in the environment or on your face, to be able to have that shared illusion. I have seen some examples, but technically very complicated. About 10 years ago at the SIGGRAPH conference, a lab from Japan was showing how you could use plasma, high voltage plasma fields to create an image that appeared to float in the real air. But the voltage was very, very high. It was around 40,000 volts. And, and they would just make a few dots appear with a lot of energy. And so that's a long way away from being a kind of hologram or something you can see floating in space without having any device. So I think it's still a long way off. But certainly there's been a lot of research done on shared projection and more unobtrusive displays, which I think are the stepping stones to get to that point.
Thank you, Mark.
No problem.
I've also seen, just as a curiosity, some recent works in cross reality. It might be related to what Jose was asking, like people using AR devices and people using VR devices, but they share the same interactive space.
Yes. So we've done some work on that as well, especially for remote collaboration, where you might have one person in AR in the real world, and then you have a second person who's remote who wants to have share that same real world location and have a VR copy of the real world and be able to interact together. There's also some other, so another commercial example of that is there's a really great application called spatial.io, and Spatial provides a shared XR experience, and you can log on with an AR display or with a VR display or your website or your web browser on your desktop or laptop or your mobile phone, and everybody can interact together in the shared space. So, when you go into the VR space, you'll see other users around, and some of those users may be on mobile phones, some may be on their VR or AR headset. So there's a lot of interesting work being done in that space. And I guess that's part of being able to make the experience more democratic and available to a wide range of users without them having to buy very high-end expensive devices.
Yes, Jorge, I see you have a question.
Yes. First of all, thanks, Mark, for your very interesting presentation today. It was very nice to watch. And yes, my question is about privacy and the technology, the problems that this technology may bring, or maybe not the technology itself, but the progress or the change on the devices we use. In my opinion, it may bring some problems. Like, for example, right now, if you want to scan some people's faces, for instance, for Instagram filters or things like that, you have to point a device to their faces. But in the future, with glasses, that might change to the point that you don't know that you are being scanned, for example.
Yes.
In my opinion, this is a huge privacy problem. And do you have any idea or any theory about how can we tackle that?
I think it's a very important question. So I was involved maybe 6 or 7 years ago with the Google Glass project inside Google, and most of you will remember that. That was the small camera you wear on your head with a camera and display, and they didn't really consider that problem very much, and then that caused there to be some big problems around commercial acceptance. And it was a bit ironic because people at the time had mobile phones all with cameras on it, but one of the big concerns people had with Google Glass is that people will be recording them in the public space. But of course, they could already do that with the camera on the phone. But when you have a camera on a phone, the person has to make some obvious actions like pulling the camera out and pointing it at you. Whereas with Google Glass, because the camera's on the head, people thought they could always be recording you. And in fact, it couldn't do that, but they didn't know that. So I think part of the problem with the privacy is looking at how we need to how people can express what they're doing with the technology, and you can become aware of what they're doing. So, for example, with the filming with the phone on a camera, then when the person pulls the phone out, it's very obvious they're going to start to record you. If you've got an AR device that can record you in secret, then that becomes a big problem. So companies, when they're designing these devices, need to be able to design ways that communicate privacy to other people. So with the Google Glass, for example, in the end, what they did is they made it so that when the camera was on, the display would always be on, and so you would see a white light turn on, and so then that the person's recording you because you saw this light go on. So the technology was communicating in a public way to everybody else that it was changing or capturing the surroundings. So I think that's one very important element of privacy. And then the second element is that the privacy standards or the in the community are changing. 20 years ago, it would be very unusual that you would be taking photographs everywhere you were going because cameras it was expensive to develop the film and the cameras weren't that fast. And now in this kind of Instagram culture and TikTok culture, everybody wants to stream everything about their lives all the time, and so their privacy expectations has changed quite a lot. So I think we have to match what the technology is showing to people, to the expectations of people, and then if we can do that, then we can help address some of the privacy concerns that will be raised. But it's still a very big problem, and part of the problem is that people don't know what technology can do. So when you've got something on your head, they don't know if you're recording them or if you're looking at information about them or what you're doing until they know more about it. So it's a very big, important problem to be addressed, I would say.
Thank you.
So we have time for just one last question. If anybody wants to share a quick question. If not, maybe we can just wrap up here.
And I should mention, if anybody has any more questions, and I'm happy to answer over email. And I'm also happy to share the slides with you, as I said before, or you can visit our website and see more of the research we're doing. There's a huge amount of work to be done in the AR/VR space. So, and we're not doing research in all the areas that you talked about, but there's a lot of interesting work that you can be doing, and if you're interested in this space yourself.
So yeah, maybe we could you could share the slide with us, and we could send it to all the people registered, so that they could all get them.
Yes, that'll be totally fine.
Perfect, thank you. So I see there are no more questions. So yeah, we can wrap up the session here. So Professor Billinghurst, thank you really, really much. It's been a great pleasure having you here today. Your talk has been really inspiring, and I'm sure many of us have a lot of ideas now to talk about. We would also like to thank the ACM Distinguished Speakers Program, as you mentioned. And of course, if you would like to talk more about ET's activities, the HCIHEALTH project, or know more about Mark Billinghurst's work, please feel free to reach out. Thanks, everybody, for being here today. Thanks, Mark, and hope to see you all soon in upcoming webinars.
Yeah, thanks a lot. See you later. Thank you so much.
Thank you very much.
Bye.